Good afternoon, everyone. We're just having some minor technical issues. So if you're not speaking, or you're not a speaker or the host, please mute yourselves and turn your video off to avoid any background noise. Um, Welcome to the IPA Power Hour webinar on the modern grid. My name is Megha Hamal. I am the Chief Strategy and Communications Officer for the Illinois Power Agency, and I will be responsible for hosting the presentation today. To get started, let's go over some housekeeping items. Again, as I mentioned, please mute yourself if you're not speaking. We would appreciate that. We will be taking questions towards the end. So there is a chat window available at the bottom of the Zoom panel. So please feel free to submit your questions anytime during the presentation. We will be doing a Q&A towards the end. Today's session is being recorded, and a recorded version of the session will be available on the IPA website under About Us events. Today's webinar, as I mentioned, the modern grid is for general education purpose only and does not represent legal interpretation or statement of policy by the IPA or its staff. As we all know, the electric grid has been the silent hero for our energy systems for many years, but it faces new challenges in our ever-evolving energy landscape. So today, the webinar will examine the role of technology in making the grid smarter, optimizing sustainable solutions and technologies to build a more efficient grid. Next slide. For those who are new to our Power Hour webinar series, here's a quick overview. We started our Power Hour webinar back in 2021 when the Climate and Equitable Jobs Act was enacted. Over the years, we have hosted more than 20 webinars on many different energy topics, and we've invited thought leaders and energy experts from all over the US to talk about relevant energy and clean energy topics. Next slide. Here's a quick overview on who we are as an agency. We are the Illinois Power Agency, an independent state agency established under Illinois law. We are responsible for two important tasks. One, to develop an electricity procurement plan, which serves as a roadmap for power procurement for residential and small commercial customers. We are also responsible for the development and implementation of our long-term renewable resources procurement plan, which serves as a roadmap for our renewable energy programs and procurements. And we've also run programs to basically support at-risk nuclear plants in the past. Next slide. With that, I want to welcome our esteemed speakers. Our first speaker for the session is Anthony Starr. Anthony serves as the Senior Advisor and Interim Chief of the Planning and Procurement Bureau at the IPA. In this role, Anthony oversees the development and implementation of two plans, Electricity Procurement Plan and Long-Term Renewable Resources Procurement Plan, to procure electricity and clean energy resources for customers of Ameren, Illinois, ComEd, and Mid-American. Anthony also oversees procurements for utility-scale solar and wind. And Illinois Shines programs and our income-eligible Illinois Solar for All program. Anthony previously served as a policy advisor to two chairmen of the Illinois Commerce Commission, and before entering government service, he spent 13 years at the Center for Neighborhood Technology. Anthony also helped start the nation's first residential real-time pricing program, as well as community-based energy efficiency and demand response programs. Welcome, Anthony. Our next speaker is Michael Jung. Michael serves as the founding executive director of the ICF Climate Center, a resource hub for knowledge and insights on climate mitigation, resilience, and adaptation, drawn from ICF's more than 2,000 climate, energy, and environment professionals. Michael's career in energy has reached across both investor-owned and consumer-owned utilities. He has served as a policy advisors to governors and has been an early team member at several successful clean technology startups. Michaels most recently served as Vice President for Government Affairs at the Pacific Northwest Generating Cooperative. In his previous role as a policy advisor, he has crafted landmark electricity legislation to the campaign and administration of Ohio Governor Ted Strickland. Michael is a U.S. Fulbright Fellow, Taekwondo black belt, former competitive ballroom dancer, and a professional ski instructor. Welcome, Michael. Our last speaker of the session is Sainab Tayo Ninalawo, a senior manager of smart grid and innovation grid modernization at ComEd, responsible for leading the team that oversees trial and development of new technologies onto the distribution system and optimizing new solutions and capabilities for customers through industry-leading engineering, evaluation, and implementation. Tayo is passionate about education and empowerment. She was the chair of IEEE-PES Women in Power, a global organization creating a movement to promote more diverse leadership in the industry. She was the FY16 VP of Outreach for the Society of Women Engineers, Chicago Regional Section, where she oversaw the high school, elementary, scholarship, and collegiate programs. Tayo volunteers with women and children around the world, providing educational and developmental support in countries such as Kenya, Peru, Australia, and India. She contributed to a hands-on project to build a school in Mexico. Welcome, Tayo, to the IPA Power Hour webinar. Now, I would like to welcome Anthony to kick off his presentation by giving us an overview of the grid.
Great, thank you, Megha, and thank you everyone for participating today. So we have the next slide, please. So to start with, since we're talking about the modern grid, or what's also sort of known as the smart grid, I thought it would be good to spend a few minutes talking about what came before the modern grid, or as I decided to come up with here, the not modern grid. So who are these two gentlemen on the slides? To the left, some of you may recognize Thomas Edison. To the right, we have Samuel Insull, who was a protege of Edison and the founder of ComEd, and really one of the architects of the modern electric utility. The reason I show them is that if you look at the picture in the middle here, this is sort of what a traditional electric grid through the 20th century would have looked like. Large power plants, transmission systems going to substations with power radiating out to homes and businesses. This is a one-way system. This was a system that both of these men would have recognized. This would be familiar to them in terms of how it works, what it does. So in terms of thinking about what the modern grid is and what we're entering into in the future and building today, I think it's important to realize how the technology evolved over time. So if I have the next slide, please. You'll see versions of this or a piece of this coming up in some of the subsequent presentations. A modern grid is something that's much more dynamic, involving lots of different resources, information and power flowing in multiple different ways. So it's a dynamic system that's very different from what we had through most of the 20th century and still have in places today. Next slide, please. A lot of it comes down to measurement and information. We'll be hearing a lot more about how these are changing and evolving. But this is one way I used to always like to think about this. Megha mentioned that earlier in my career, I worked on what was known as real-time pricing, which was the ability to price electricity at an hourly level rather than sort of overall consumption. And measurement, and I actually dusted off a few of these pictures from a presentation I did probably about 15 years ago. And I think this is the key concept here, that if you look at an electric meter from the beginning of the 20th century and the end of the 20th century, they're basically the same device. The fitting and glass is maybe a little different, but basically this is a device that just measures cumulative consumption. A modern electric grid with smart meters that measure energy in granular amounts, transfers that information wirelessly to the utility, is a transformative device. And let me sort of talk about a couple different ways in which this is important. One is that this gives us different options in terms of how we price and measure electricity. But it's also key in terms of thinking about the information that a utility needs in order to run their electric system. Without a modern grid, without smart meters, other devices that you'll be hearing about on the grid, what happens if your power goes out? You call your electric company. If they get a phone call from just one person, they think maybe, they may look into it a little bit, but it's probably just something that happened at home. If you get calls from multiple people, you begin to look at it. But think about most of the 20th century. How would you do this? You would probably have to get out paper maps, look at who is calling in to say there's a power outage, figure out where those are clustered, then send trucks out to look for where the problem is. With meters that only record little bits of information, the ability to sort of have a modern dynamic system that responds to customers' needs was very limited. So a key part of the transformation to the modern grid is having this better information, this ability to be more responsive. This can come out in a number of different ways. Next slide, please. What can the modern grid do? So up on the left, I have our friendly squirrel, common cause of electrical incidents where they nibble on the wrong wire and end up looking a little different than this. So again, the modern grid is the ability to sort of respond to specific outages caused by squirrels, tree limbs falling, etc. All those sorts of things that happen in the course of day-to-day life. We also have to confront the realities of climate change and weather volatility and how that will impact the electric grid and the need to have more ability to understand what's happening in the grid and be able to respond, dispatch crews faster to fix things, be able to dynamically redeploy resources. So climate change, again, is a key driver for the need for the smart grid. But then from the customer point of view, this also enables a whole wide range of options. Real-time pricing or time variant pricing with a number of different variations. Illinois has been a leader in real-time pricing. Having the ability to price electricity at an hourly basis, have the ability to measure that and send information out to customers to respond. This is something that's enabled by the smart grid. The increasing penetration of solar at homes and businesses across the state is something also having better technology available on the grid to manage the power flows from that, a key aspect of the smart grid. And then to the right, electric vehicles are getting more and more common. Right now, we really are still in the era of electric vehicles taking power from the grid. One of the sort of holy grails of smart grid is the idea that electric vehicles ultimately become resources that the grid can call on to bring power back up to the grid as needed. This all requires much more advanced technology than the traditional grid that Insola Edison would recognize. So part of the potential of what we're talking about here is the ability to have these sorts of dynamic systems available. So as a state, we are looking at a variety of different policy options going forward. How do we better include battery storage, for example, into the grid? All of these are key policy decisions that are really important for us. And the evolving modern grid will be a key aspect of letting that become possible. We have utilities that have pretty much completed the deployments of smart meters. So we do have a system that looks very different. If you go back to those pictures of the electric meters, we don't have the spinning dial electric meters in use very much anymore. So we have a lot of pieces in place, but there's still a lot to be developed and built out. There's still policies on who owns parts of the grid, who controls things, what are sort of privacy around information. All policy issues still kind of actively being debated and will continue to be debated in the years to come. So with that, I'll end and turn it over to Michael.
Thanks, Anthony. Thanks for setting the stage. My name is Mike Jung, and I am the Executive Director at the ICF Climate Center. For those of you who know ICF, you probably know it as a consultancy. My role at the Climate Center is to essentially run a think tank within the consultancy. Rather than being client-facing, we are public-facing, and we do thought leadership, some of which I'll share with you today. Next slide, please. Preview, we're going to talk about digital twins, and that's what's depicted in that photo there. But let's begin by sharing some findings from a report that we've recently issued on U.S. climate goal progress and opportunities. To put it succinctly, we are putting a lot of eggs into one basket when it comes to how we are going to meet our climate goals as a country. You see here a chart showing the gray line, which was our trajectory in terms of carbon emissions prior to the BIL IRA policies. The yellow line shows where we're headed with the current policy tools that we have. And the blue line shows us the diversified goal pathway that's going to get us closer to those green dots that are our targets for US GHG emissions in 2030 and 2050, respectively. In order to get from the yellow line to the blue line, we're going to have to put a lot of eggs into the one basket that is the grid. Next slide, please. Which eggs are we putting into that basket? Well, we find three major areas that we're going to need to invest in and be highly active in order to get to those climate goals. The first is in electric vehicles. We're going to need over 100 times as many EVs by 2050 as we have on the road today. Obviously, electric vehicles are electric. They're powered by the grid. And so we're going to have to dramatically rethink how we operate, build, manage, and plan this grid so that we can power the transportation sector, which is a huge part of how we're going to get to our climate goals. Next slide, please. Building decarbonization is the next leg of this stool. We find at our analysis that we're going to need over 1 billion building decarbonization measures. These are things like heat pumps, rooftop solar panels, energy efficiency investments, but we're going to have to touch pretty much every building in the United States and deploy some measure, usually a combination of measures, of building decarbonization tools in order to bend that curve from the yellow to the blue that I showed earlier. Next slide, please. And not only are we going to be electrifying the transportation sector and electrifying the building sector, but we're also going to have to clean up the grid that we're going to be using to electrify those parts of our economy. By 2050, we find that we're pretty much going to have to take unabated fossil fuels out of the system and replace it largely with renewables. 85% by 2050 is what we find in our analysis. Next, please. So if we're putting all of these eggs into the grid basket, well, what does that mean for the grid? What we see here is some analysis from the International Energy Administration, International Energy Agency that was recently released, assessing the state of the grids and trying to make some guesses as to what we're going to need to do to these grids to meet our climate and energy goals going forward. The blue line at the bottom, I draw your attention to, is existing distribution line miles. And you see this is going down. The grid is getting older, and we're going to have to retire a lot of this grid that we currently have. This is for advanced economies, I should note. But the US is pretty typical in this curve. A lot of the grid that we have is going to be expiring by 2050. We're going to have to replace a lot of it. And so you see sort of the teal line or the teal wedge that is largely replacing the grid that we already have. You hear a lot of news today about transmission and interconnection and how are we going to build the high voltage equipment. But what you see when you look at the line miles chart here is that the preponderance of work really is happening at the distribution level, the capillaries of the grid, and the capillaries are more challenging in many ways. There's a lot more of it. We don't have the visibility into it. And we certainly are going to have to change dramatically the way we own, operate, manage that part of the grid. And as if that weren't hard enough already, replacing most of the existing distribution line miles with new distribution line miles, we know that because we're going to be putting so many eggs into the grid basket, we're going to need more distribution line miles. And that's that orange wedge that you see on top. We're going to have to grow the distribution grid. And overall, it looks like we're going to have to, significantly increase from our current capacity of just over 30 million kilometers of line miles across the grid as a whole to closer to 50 million kilometers around the developed world. The United States is a big chunk of this, and our trajectory is likely going to be along these lines. Next slide, please. As the distribution system grid evolves and gets rebuilt and replaced, so will the nature of the resources on that distribution grid. For a long time, as Anthony showed us, the distribution grid was just that last mile of delivery. It was a one-way street. But going forward, we're going to see lots more what we call distributed energy resources These are things like electric vehicles, energy storage, rooftop solar. This is all going to be landing at that edge of the grid, on the distribution grid. That one-way street is not only going to turn into a two-way street, it's going to turn into a very busy intersection, more like a roundabout than anything else. Lots of things going in, lots of things going out, unpredictable at best. You see the utilization of distributed resources will increase over time. The big star there in the middle is FERC Order 2222, or 2x4 as I like to call it. That is enshrines in policy the integration of distributed energy resources into the bulk power systems operations. The grid is going to get more complicated, and most of that complication is going to happen at the edge of the grid at the distribution level. Next slide, please. So what does that mean? That means that the lines between generation, transmission, distribution, and behind the meter that Anthony showed us in the beginning here, those lines are no longer solid lines. They're getting blurrier and blurrier. And not only is it's not going to become a one-way street, but it's going to become a pretty complicated dance that we're going to have to learn how to do. Here we see a lovely chart from the Lawrence Berkeley National Lab folks on what are we going to need to do in terms of changing how we think about the timeline of interactivity of the grid. In the beginning, we would basically use a planning horizon. We were thinking years, seasons, weeks at the most granular. But as that grid becomes more dynamic, we have to start evolving our thinking and evolving our capabilities, going into the shift and the shed and the shimmy. This is a pretty complicated dance, and we're going to have to learn how to dance it. We're going to have to start thinking in terms of seconds or even sub-seconds in order to meet the needs of the modern grid. Next slide, please. So how do we know where we're going if we've never been there before? Well, I'd like to use an illustration here, which is to draw an analogy from the evolution of mapping. If we don't know where you're going, it helps to have a map. And in this case, we can look at the history of sort of how we got from point A to point B as drivers, as perhaps an illustration to help us understand what the next grid of the modern grid is going to look like going forward. Some of you may recognize the Rand McNally Road Atlas. This is what I grew up with as a kid. If you wanted to go on a road trip, that's what you pulled out. And you took a look and you just figured out, okay, which page am I on? Which page am I going to end up on? And how do I connect the dots between the two? It was a very manually operated, error-prone process. It was fun, but it certainly wasn't efficient. In the 90s, I recall a huge step forward was when you could go down to the local AAA and get what you called a triptych. And basically you told them, I want to go from here to there. And they would go into their little computer system and generate that little map that you see on the left-hand side, bottom picture, that gave you this kind of predictive map. Okay, if you want to go from A to B, here is the route that our system tells you that you should take. And we're going to highlight it for you. We're going to show you places you can get gas and whatnot. But that's this predictive map that we've generated for you. So no longer did you have to figure it out yourself. You could actually use this system, this triptych system, to give you a plan. Well, of course, the internet happened, and before you know it, you could do MapQuest, and you could do that yourself. You didn't have to drive down to the AAA to get a triptych. And the MapQuest system put that power into your own hands, which seemed like a revolution until the first dashboard GPS systems evolved and arrived. You see that in the middle picture on the right-hand side. And that dashboard GPS was transformative. It actually knew where you were in relation to the trip that you were planning to take. It could tell you where on the map you were, and that was a revolution. I remember thinking, we have arrived. Before we know it, we're going to have hover cars and whatnot. But really, the where we are today is even more profound as a change, which is that not only do our systems, in this case, Google Maps on the bottom right, not only does it know where we are, but it has a sense of where everyone else is too. And it can tell you when you're off the route. It can reroute your route for you if you miss a turn. It can reroute it in case traffic gets bad and it finds a better route based on real-time conditions. That is where we are today. And this journey from the Rand McNally Road Atlas to Google Maps of today is emblematic and representative of the kind of journey that we might expect the grid to go for go down, going from where it was to where it is going as a modernized grid. Next slide, please. So we've talked about what is essentially a digital twin for the grid. A digital twin is a digital representation of a physical object. In this case, the grid is the most complicated, most complex machine ever built. And a digital twin lets us essentially have a digital version that we can use as a simulation. The good version of this lets us have a visualization of what's happening. We'll have sensors all over the grid. We'll be able to collect data. It'll tell us what's actually happening. And this is like moving from the road atlas to the triptych. Now we have a plan. But even better is a predictive system. This tells us when something is wrong. This tells us how this map is changing over time. We can plug in different potential routes. We can do what-if analysis on the grid. Lets us start managing our assets in response to actual conditions. It gives us a prescriptive sense of what's happening on the grid. This is like first generation dashboard GPS. And going with good, better, best. Best is taking those tools and trusting them, empowering them to become autonomous, letting these distributed energy resources become transactive with each other at the edge of the grid, giving us instant interconnection for DERs, for example, rather than relying on interconnection studies to take days, sometimes weeks. Now we can probably do that instantly in real time almost. We can do scenario planning. We can say, what if this transformer went out? What if this asset went down? What if this line failed? You can do that in real time, and you can actually see the system change on the digital twin without having to mess with the actual grid. It becomes interactive as opposed to just prescriptive. And this is sort of like Waze. If you've ever used that app, it tells you in real time what's the best way to get from A to B as the real-time conditions change. This is what I would suggest is where we're headed in terms of the digital twins for the grid, in terms of the modernized grid. And with that, I'll hand it over to Taiwo.
Good morning, everyone. Can you advance the slide, please? Yeah, thank you for having me. I think you heard from Anthony about the proliferation of electrification and DERs in our system, so distributed energy resources on the grid. And you also heard a lot from Michael about the need for an advanced grid that can allow for two-way power flow. If you go to the next slide, I'll give a quick overview of ComEd. I think most of us know about ComEd. Next slide, sorry. Yeah, so ComEd delivers electricity to more than 4 million customers across northern Illinois. We manage about 9,000 miles of power lines in 11,000 square mile territory. What's really key here that segues into the presentation today is that in 2012, we launched one of the largest grid modernization programs and smart grid programs in the nation. I am part of that smart grid team. We're supporting thousands of job creations to drive innovation to meet the evolving customer needs and also to meet the evolving needs of the grid. Next slide, please. Yeah, so I'm going to touch just very little on this slide. I think we've heard a lot about the change in grid. One perspective there is the climate change impacts and increasing pressure for change. Over the past few years, utilities have seen a very rapid change with three key themes being, climate change, decarbonization, and clean energy. Weather events and storms are becoming very, very impactful more than before. I'm showing here a 2021 study that was done by the National Centers for Environmental Information. And it's really showing, what the change has been over the years, especially when we look at 2021, coming to be the second to 2020 in terms of number of natural disasters that we saw, 20 versus 22. And third, when it comes to the cost of those natural disasters, for about $145 billion. What really made 2021 stand out was the diversity of disasters that we saw, from winter storms, tornadoes, wildfires, 8 severe weather storms across Midwest, Illinois, some of which we also saw here in the Chicagoland area and within our ComEd territory. We've worked really hard over the years to build, record-breaking reliability in ComEd and for all of our customers, with investments, and you saw in the beginning of the slides here with Anthony's slides when it comes to AMI, so advanced metering infrastructure, your smart meters, and also distribution automation devices. In 2020, August of 2020, we saw one of the many examples that may come of extreme weather, which was the 2020 derecho that happened here in Chicago. The derecho storm hit northern Illinois with over 20 storms across Illinois, Wisconsin, and I believe Michigan, Indiana, I apologize, impacting nearly 2 million homes. Our service territory here across northern Illinois alone saw about 13 of those tornadoes, with wind gusts up to 110 miles per hour, leaving hundreds of thousands of our customers without power, which we could restore very quickly due to the work we've been doing to modernize the grid, the advanced technologies we've been piloting and scaling for the grid. Knowing this, it's really imperative that as we design the grid for planning, for operations, for maintenance, we continue to design a grid that's reliable and that can be and enable a resilient power grid, really withstanding all of these adverse weather conditions that we may see more of. Next slide, please. So here are some of the utility trends that really drive the smart grid work that we do here at ComEd. ComEd actually has a roadmap for an equitable, orderly transition to clean energy. We like to think about transforming and really transitioning the energy industry. And a lot of that roadmap just sets the vision for our investments throughout the next few years in critical infrastructure, customer programs that can advance the key goals, including that of CJA. And I believe you heard about CJA earlier, the Climate and Equitable Job Act. The 5 key trends are really based on, entire sectors of our economy are electrifying. With the shift to zero carbon, we continue to see an explosive, really, growth rate of EVs on the system. The number of registrations in Illinois increased by over 40% in 2021, according to the data from the DOE. The second trend being that renewables require a decentralized approach. Anthony talked about the need, for two-way power flow. That's really driven by the proliferation of renewables on the system. So DERs, distributed energy resources throughout our territory, require that two-way power flow, and the grid was not designed for this. So really thinking through how do we build those capabilities and design the grid to accommodate two-way power flow, to accommodate those DERs on the system. I touched on the third point on the earlier slide, which is really about weather and the climate change impacts. The fourth one here is our customers are smart, right? They're starting to see that they have options and information that enables them to use energy in a different way and to understand the incentives that change the way that they use electricity. And lastly, a vast array of technologies can be leveraged to build a stronger grid. I'll touch more on those technologies on my coming slide. In addition to the trends that we see here, the 5 trends that I've listed, to the right side of my slide, you also see that we're having an increase in interconnection applications due to the passage of the Future Energy Job Act in 2016, FEJA. It will continue to grow with the implementation of CJA over the next several years. Incoming solar applications for ComEd are on record pace in 2023. We're anticipating volumes of about 20,000 by the end of this year. With that, we have to be dedicated to innovation that's using the latest technology, the tools, software, working very closely with our IT and security teams to ensure that we're developing more applications to optimize the grid and also continue to accelerate an equitable transition to cleaner energy. Next slide, please. Some of the challenges that we see here when it comes to going from that, one-way power flow to a multi-directional or two-way power flow is really, the grid is a complex system. A quick example is here, we have one system that has very varying needs. I mentioned earlier that we manage 11,000 square miles within our service territory. That includes about 66,000 separate miles of primary distribution, and 52% of that is overhead, with the remaining 48% being underground. Each of those circuits have very unique customers, a unique mix of different load profiles. It's really important that as we think through technologies, applications, and the different trials for this technology, we're keeping in mind how different the different areas of the system are, the different loads that we have, whether it's data centers, residential load, industrial customer load. They all require very different things. And so we're keeping that in mind with those trials that we have. Next slide, please. So when we think through, an evolving grid and the components, a lot of what I'll focus today on is about data and the different tools and sensors that we have for collecting data. Data collection, really think through about, we have a variety of sensors right now with different granularity and data collection rates. So measurement rates that allow us to see different parts of the system. The system architecture must support collecting that data from enough sensors to deliver applications while also meeting performance requirements, because our customers want to keep the lights on, right, for availability, for latency, but also it's important that these measurements across the different sensors that we have, whether it's visual measurement units, smart inverters, smart meters, and the rest listed on the slides here. I want to go through all of them. It's really important that this data is synchronized across all of the systems. So the need for synchronized measurement data shows that equipment vendors of devices, such as the ones I've listed, must work very closely with the utility, with our IT system, with our IT partners. One that I will touch on later on are the facial measurement units, which are the PMUs. When we think through the transmission of the data and the communication infrastructure, as we know, we have a lot of radio systems today. Communication infrastructure to transport data will need significant investments and improvement to support the widespread deployment of the synchronized measurements on the distribution system. And so looking at the slide again, that's about 7 different kinds of sensors listed on there. All of those require fast communication. The communication architecture will need to be located between the field measurement itself, which is, grid edge measurement, close to the load, close to the customers, and the substation, which is centralized. And between the substation and also the SCADA control systems and our operating control systems. And so that information needs to be able to flow both ways and to the control systems. In addition to that, the latency, like I mentioned, and the data availability are really critical. Data must be collected and transmitted to these control centers in real time so that we can take real-time measures to correct whatever issues we're seeing. We need to do analysis, and control actions must be implemented in real time. It also requires the implementation of a highly reliable and low latency telecommunication system. So when we think about that, it's fiber. Fiber optic communication can complement wireless communications that we have today for critical measurement nodes that require higher measurement reliability and that low latency. The last part of it is, it's one thing, and it's really cool to have all of this data sitting around. It's cool to have this data transferred to the control centers. It's really about what we do with the data, how we use the data, how we realize the benefits from the data and from the different sensors and tools that we're deploying. Data measurement, data management, data utilization is really critical here. This really focuses on automation and control, converting that data into actual useful insights for our operational effectiveness. Whether it's the operating teams, the engineering teams that are looking at this data, we need to be effective in how we use the data. Again, going back to using that data in real time. Increasing visibility into system operating parameters, greater control to optimize energy efficiency, and to also ensure reliable electricity delivery. I'll talk about our DERMS platform in a few slides when we think through how we actually optimize the data today on the COMET system. Next slide, please. So here, just very high level, just a few solutions for an evolving grid. I wish I could put this image that I have on here next to Anthony's image, the black and white one, because you really get to see the differences in what the grid was hundreds of years ago versus what it needs to be and where we need to get to. Some of the solutions for an evolving grid that we see today is regards to distributed energy resources and electrification. They will be vital in providing the nation with clean energy via the distribution system. A lot of thoughts have gone into the transmission system. It comes back to the distribution system. Emerging active distribution systems are envisioned to include greater penetrations of the DERs, whether it's PV, wind, battery energy storage systems, for non-wires alternatives, electric vehicles, and actually active consumer participation. To accommodate all of these DERs, we need a lot of changes in distribution network planning, operation, and protection and control methods for the grid. Specifically speaking about control methods, we need better sensor coverage that provides fast and detailed distribution system operation measurements in real time. advanced monitoring really becomes necessary as we evolve from that passive, radio circuits with unidirectional power flow to a more complex grid that's meshed, which is key, with mesh networks where power flow, magnitude, and direction are driven by the operation of the distributed energy resources on the grid, new apparatus, and of course, the electrification connections. Next slide, please. Before I touch on the different trials, pilot, and demonstrations that we have here, I think it's key to note that, again, utilities are evolving. In order to evolve effectively, it requires partnerships and collaboration with academia, national labs, the DOE, other industries, IEEE, EPRI, whoever it is. We continue to learn a great deal about enhancing the grid and informing grid planning for a more sustainable future through these partnerships. I've listed some of those partners on the slide, and I think I'll talk some more about the work that we've done with them in the upcoming slide. But it's really critical that we keep this partnership going so that we can continue to have that external exposure to what others are doing, benchmarking with these different groups, other industries, other countries, and then collaborate on what we can bring back here to enable this two-way power flow and the proliferation of DERs on the system. Next slide. One of the projects that you've probably heard a lot about is our Bronzeville Community Microgrid. In February 2018, the ICC, the Illinois Commerce Commission, granted ComEd's request to construct, operate, and collect data from the Bronzeville Community Microgrid. A microgrid is really just a localized power grid that can disconnect from the traditional utility to operate autonomously and help mitigate grid disturbances and strengthen grid resiliency. So it's really all about resiliency when we go back to this adverse weather events. The Bronzeville Community Microgrid is an opportunity for us to demonstrate how community microgrids can enhance the resiliency of an urban area as it confronts the different stresses and pressures based on weather and other factors. Again, this is a microgrid that's going into an already developed urban area within our service territory. I'll talk more about the challenges there. But the goal of this is really designed to seamlessly integrate renewable generation and battery energy storage into the grid while allowing for systems to island for added resiliency. Some of the, when you look at the top line, and I think I'm using my pointer here, but you can't see that, you can see our DERs, distributed energy resources, on that top circuit within the microgrid. The other things that you see on this image are the critical customers that we're serving, and I'll touch on why that's important. And then to the right side of the image is IIT, the microgrid within the Illinois Institute of Technology, which allows us to not just build a microgrid, but also build capabilities to cluster microgrids. So the goal here is, once we complete the construction of our microgrid, in 2025, once IIT's microgrid is completed, we do plan to use our master controller to cluster both microgrids. The microgrid today is being deployed in two phases. The first phase included a 2.5 megawatt portion of the feeder. The top feeder that I talked about earlier, along with a solar PV system and the battery energy storage solution. The PV is 750 kilowatts AC, installed on the roof of 17 buildings at the Chicago Housing Authority. And so again, partnership with the community was really key there for us in building this microgrid. We're really learning about integrating customer-owned DER assets onto the microgrid. It's 17 rooftops, and then we also have ground solar, owned, operated, maintained by the Chicago Housing Authority. The battery is a ComEd-owned system. It's a Lockheed Martin lithium-ion battery, 500 kilowatts, 2 megawatt-hour system. What that means is it operates for 4 hours. Upon completion of the third generation assets, which is about 4.8 megawatts of natural gas generation, should be done at the end of this year, installed at the end of this year. We'll have all of the DERs within the microgrid livened. I think I see a question in the chat. The microgrid will be serving a total of 7 megawatts of load within the footprint. The microgrid, as I mentioned earlier, is strategically placed in Bronzeville due to the partnerships that we've built within our Bronzeville community. So we have, didn't put it on the slide here, but the Community of the Future initiative, which the goal really there is to develop partnership with different communities. We have one in Brownsville and one in Rockford, and to drive that collaboration when it comes to piloting new technologies, but also an equitable energy transition with the communities. Within the footprint for this microgrid, we have critical customers such as the Chicago Police Headquarters, the Public Library, the Chicago Housing Authority, like I mentioned, College of Optometry, and the rest are listed on the slide here. So not only are we building a microgrid for resiliency, we really are building community resiliency. Our approach here is that we provide a solution that further minimizes our customers' outage times while also providing a safe haven for the surrounding communities in case of any grid emergencies or any weather or any adverse weather impacts to the grid. The microgrid was constructed around renewable penetration. Really, as we think through the grid needs today, it's all around renewable penetration. Due to these reasons, along with this, we've developed a microgrid master controller in partnership with Siemens. And what that master controller is doing, it's monitoring the grid, the microgrid itself, and adapting to changing conditions of the grid caused by the DERs. And so the solar PV coordination with the battery and with the natural gas generation. What's also really important and complex about this controller is that, again, it's being put in a system of the grid that's already built out. So we have voltage optimization capacitor banks out there. We have distribution automation devices and other grid edge devices on the grid today, right? That controller has to work in unison with to ensure that we're optimizing the DR assets within the microgrid and we're able to island autonomously without any impacts to the customers within the microgrid. Next slide, please. I'm gonna go a little faster. I'm watching the time here and I have 14 minutes. Thank you. Oh, 4 minutes. Okay, so facial measurement teams, I'll talk very quickly. One of the things we're doing here with PMUs is really Comet is looking at a 3-tiered approach to the deployment of PMUs. One of them is a substation level approach. We understand that these deployments provide visibility at the highest layer of the distribution system. So substation level, we're enhancing the 12 kV and 34 kV relay packages at that substation with PMU functionality. At the feeder main stem level, working very closely with existing interrupters to deploy PMU functionality on the interrupters. And then on the feeder edge level, also put in micro PMUs closer to DERs and to the load. The goal here is really to continue to have a high visibility and collect data. So with this 3-tiered approach, we have a mesh of data that we're collecting, right? When we think through that on the next slide, that's where analytics comes in. With our PMU analytics, all of the sensors, all of the data that we're getting, we're building a high quality data analytics dashboard and program that helps us realize the full benefits of the deployed infrastructure that's on this slide. Over 5 different applications. Next slide, please. Those applications include DER integration, distribution system operations, wider area monitoring, asset management, and then planning and analysis. We're on track to developing this PMU analytics dashboard. It's a predictive grid dashboard. So again, getting information in real time and reacting in real time, for lack of a better word, by the end of the year. The other slide, the next slide, talks about our battery energy storage system solutions as a solution for grid planning. So thinking through non-wires alternatives. As we prepare for these extreme weather events, we're investing in it to increase resiliency and reduce future peak demand through energy efficiency methods, battery storage, managed electric vehicle charging, and other solutions. These are the different technology pilots that we have today within Comet for batteries. You know, these solutions range from batteries for capacity deferral at the substation level, capacity deferral at the feeder level, 500 kilowatts battery that we have. We have smaller batteries for community energy storage solutions where we're trying to think about pocket reliability issues and how we mitigate those using battery energy storage. So charging these batteries at normal hours, and then when there's an outage, supporting those customers who may be in faraway areas with the battery. And then we also have additional demonstrations supported by the DOE when it comes to integrating high penetration distributed energy behind battery. Again, solar that's owned by customer, battery owned by the utility, and really learning on how both of these can work together. We're building these capabilities with goals of developing standardization and a framework for batteries for the utility, and we can share more about that later on. But very lastly, if we go to the last slide, I want to talk about our DERMS solution. distributed energy resource management systems on the next slide. It's really about technologies for monitoring, control, and market integration of DERs. DERs are typically today, limited by worst case scenarios requiring expensive infrastructure upgrades to mitigate them. Our DEM solution is centered around enabling interconnections and managing this DER to mitigate system constraints without the customers having to pay bullocks of money to enable their interconnection to connect to us. The goal is really to increase the hosting capacity for this DER, to reduce customer interconnection cost, and then have a reliable mechanism to control these DERs. Some of the pilots that we have today is within our Mendota area. DERMS Mendota was really designed and implemented with the intent of ComEd developing more DERMS capabilities. We've been operating the DERMS Mendota since 2021. Right now, we have about a total of 6 megawatts of solar integrated into our DERMS system, with 2 more customer interconnections going in by the end of next year, for a total of 9 megawatts integrated onto the system. I'm going to stop here because I know I'm at time and I want to be respectful of any Q&A sessions, but I'm happy to take any questions during Q&A.
Thank you, Tayo. We wanted to do this webinar Q&A a little bit differently and have Anthony moderate the discussion. If anyone has any questions, this is your time to ask the questions to our experts.
Great, thank you, Megha, and I'll give a minute for people to put in questions. But I guess I wanted to start out with a question for both of you, which is about timing. The ComEd microgrid, I believe, was approved in 2018. Here we are nearing the end of 2023. There's a lot of exciting momentum here, but thinking about how quickly the tech industry moves, and thinking about how slowly often the electric industry moves. My point I was trying to make in my comments was that pretty much for 100 years, there was a lot of things that didn't change much. There were obviously aspects of the electric system that did change over the course of the 20th century. What challenges do you both see in terms of sort of how utilities go about testing, deploying, getting regulatory approval for new ideas to modernize the grid versus how other parts of the economy are operating where they have different sort of constraints and opportunities?
Yeah, great question, Anthony. Since you brought up the microgrid, I think I can speak to some of the challenges that we're seeing with the delay there. And I think it will answer also your question on the importance of partnerships with our regulators, with our cities in deploying new technologies. One of the reasons that the microgrid is actually taking so long is due to city permitting for the natural gas generation that I mentioned. And so that's 4.8 megawatts of natural gas going into an urban area. We had to go through zoning approvals, noise testing approvals, city permits to construct that. That took a very long time. We finally received approvals from the city this summer, I believe August of 2023, and I'm on track to complete it this year. So a big piece of that, we were backed by our regulators to go ahead and construct this microgrid. We've been very lucky to have support for the technology demonstrations that we have, but it really comes down to also partnership with the city. That's been the biggest delay for our microgrid here in getting those city permits and approval to actually move forward with construction.
Anthony, you raised a really powerful point. Having been involved earlier in my career with some of the clean tech startups that have worked with ComEd, among many other utilities along the way, I would say that wherever possible, future-proofing strategically is an important thing to do. As a specific example, we know that the kinds of things that we're going to connect to the grid, especially in terms of distributed energy resources, are going to evolve over time, and that's how it should be. But to the extent that we can build communications infrastructure that connects these devices and do it in a way that future-proofs it so that it's agnostic to what kind of devices are being connected over time. As a specific example, the protocols and the standards that we use to exchange data across communication networks needs to be pretty universal. It needs to be open standards based as much as possible, so that no one gets locked into something that's proprietary, that's dead-ended, that is lives a useful life that's measured in years as opposed to decades.
Yeah, I think that's a really important point. We had some issues about a year and a half ago in some of our solar programs as the 3G wireless network was being turned off. And there are many, many, many solar projects out there that have reporting systems that use 3G communications, this became a bit of a crisis for some vendors in terms of needing to be able to get out in the field and replace those. The future proofing hadn't happened, obviously exacerbated by supply chain issues and things like that, and ability to get into people's homes during COVID lockdowns made it more difficult as well. But I think that, to me, that's a great case study in sort of the future proofing that you described. Question came in through this. Sorry, go ahead.
I was going to add to what you said regarding future proofing. So I think there's an opportunity for utilities to partner even closely with vendors and manufacturers of technology. As we're starting to see more OT devices, so operational technology and security concerns with those devices, it's really important that we're working upfront with these vendors to ensure that they're meeting security requirements for utilities, right? Otherwise, we start to get those technologies onto the system, and then it takes a really long time to get approvals, exceptions, and then pilot them.
Great. So a question that came in through chat, I think is an excellent one. So I'll just read it. Does ComEd have awareness of DG on the grid? That is, does ComEd see the smaller DG projects like commercial and residential solar and storage as having the same value to the future of the grid? And how is ComEd promoting more of this?
Yes, we do have awareness of all of the DG on the grid. We have an interconnection team that gets all of those applications, and it goes through our planning processes based on the level of the size of the interconnection, but we do have awareness of all of them on the system. With regards to what ComEd is doing, and trying to read that question again, of promoting more of this on the grid. Our customer solutions team works day in, day out on rebates for solar, Illinois Solar for All. So there's a lot of rebates out there. We do ensure that we are passing those along to our customers, a lot of education, a lot of communication with our customers. We have whole teams dedicated to supporting the proliferation of DG on our system and supporting our customers through the process.
But today, the awareness of DG on the system is not necessarily real time, in the sense that ComEd has awareness of the production in real time. That's more something that will come through smart inverters, if I understand correctly. Sorry, yes, smart inverters.
I would add, Anthony, that I think ComEd is doing better than most of the industry when it comes to that visibility, because ComEd has invested into infrastructure that allows for cutting edge kind of capabilities. That said, a lot of utilities don't know what they don't know. They know what gets requested to be interconnected, but there's a lot of stuff that happens behind the meter that utilities simply don't ever hear about because they're never asked for permission. And so an important capability of digital twins is to create that digital simulation so that as the utilities sensors out in the field detect anomalies from what the twin says this is what should be happening, that gives the utility the ability to say, something is now different over here. You can go to that customer or that premise and you can find out, oh, now there's an EV there. Oh, now there's a battery energy storage device there. Oh, now there's a DG device there. It may not have been formally, kind of put in for on the interconnection queue. That said, this kind of stuff does happen, and having digital twins gives us utilities better capabilities to see where something is different from what they expected.
That's a great segue into my next question. Since you work nationally and internationally, I'm sort of curious your perspectives on, we're ultimately the Illinois Power Agency, so while we care about the rest of the world, our focus is primarily on Illinois. What do you see in terms of progress in Illinois? I mean, we weren't the first to sort of invest in smart meters, but ComEd's initial pilots were pretty early on from an sort of national perspective. I'm curious then, where do you see Illinois and the Midwest more generally sort of standing in terms of the overall arc of grid modernization nationally and internationally?
That's a good question, Anthony. It's uneven, right? There are certain places that are moving faster than other places, but in only certain areas. I would say an area where Illinois is ahead in addition to sort of the infrastructure side of things. I think on the equity front, there is an awareness that I think is further out ahead than many other parts of the country, that how we do the modernization of the grid needs to be done consciously so that those who have been disadvantaged in the history of the grid do not continue to be disadvantaged. And in fact, if we can, bring them back up into a more equitable posture with regard to how they interact with the grid. To be specific, the folks who often have a hard time paying their bills often are the ones struggling because the buildings that they live in are the least efficient, the least well sealed. And if we are then approaching them to install renewable rooftop with incentives, it behooves us, I would say, to make sure that we're doing everything we can so that that energy that we're installing for them doesn't get leaked out through a building that could have been retrofitted at, through a similar or related touch point. Illinois, I think, is doing better than most places, but, we all need to be doing better, including Illinois, when it comes to making sure that the transition in the energy front on the climate challenge is equitable.
Yeah, I think that's a key point. I mean, obviously, one of the center points of CEJA was the equity focus. And that's something we continue to focus on in our programs. That would be very important. One last question that came in the chat would be, again, sort of maybe more of an international perspective in terms of, you see, is Europe's power grid facing similar challenges? Are there technologies used in Europe, or I suppose elsewhere in the world, that mitigate those challenges that may be different from what we're doing in the US?
Interesting. The European grid is substantially different, but for reasons that there's a lot of temptation to say, oh, these folks are doing it this way or using this policy or that technology. Let's just cut and paste. But Europe has, fundamentally different sort of physical infrastructure. Their population density is different. The layout of their urban topography is different. They're operating on a different frequency as a grid. So the systems are different. What the Europeans, I think, are doing that we can learn from, though, is they're doing a pretty aggressive job leaning in towards interconnecting their larger high voltage transmission grids. We complain in the United States here that, oh, the wind doesn't always blow and the sun doesn't always shine. That's true only at a certain resolution. Somewhere the wind is always blowing. Somewhere the sun is always shining. And if we can do as good a job in terms of connecting our high voltage grids, so that the United States right now has 3 big kind of high voltage bulk power systems. If we can interconnect them better, we can lean on each other. We're the country that said, a house divided cannot stand. A grid divided also doesn't stand as well.
Great. That's a wonderful way to end today's Power Hour. Megha?
Yes. Thank you, Anthony. Thank you, Mike. I love the analysis of GPS for the grid, and thank you, Tayo, for just talking about the microgrid and how it's addressing the needs of communities and sort of reimagining the future of energy moving forward. So with that, I want to thank our esteemed speakers for taking the time to share their knowledge on the topic of the modern grid. I also want to thank all the attendees on behalf of the Illinois Power Agency for coming in and joining this wonderful session. I hope it was helpful. Here's contact information of our speakers. If there are any additional questions, please go ahead and email them. And a copy of the recording of this Power Hour will be made available on the IPA website under About Us events. With that, I want to thank you all. Have a lovely weekend, and we will see you at the next Power Hour. Goodbye.